Good evening, all. We will wait for 5 more minutes. If we will see if any other one joins, then we will start. Okay, so we will start now. Uh, in previous lectures, we have learned about the biological transformations. We have learned about one type of biological transformation, which was composting process, or we can say the other form of composting process was vermicomposting process. Okay, so now we will talk about the second type of biological transformation, which is basically anaerobic digestion process. So, in anaerobic digestion process, what we do uh, while we were talking about the vermicomposting process, it was all about the decomposition of the solid waste in the presence of air. Okay, but when we are talking about anaerobic digestion process, it is defined as the decomposition of solid waste uh, in absence of air. Okay, so the transformation process will differ if we are going to compare it with composting process. So in anaerobic digestion process uh, there will be no oxygen presence. Okay, so due to that absence of oxygen, there will be no generation of CO2 gases. Okay, there will be the generation of methane gas, or we can say CO gas, or maybe some other type of hydrocarbon gases. But there will be very minor formation of the CO2 gas. Okay, so the definition of the anaerobic digestion is it is a controlled process involving microbial decomposition of organic matter in absence of oxygen. Okay, so when we are not providing any oxygen element to that, okay, so that will convert the compounds into the sulfate form or maybe in nitrate forms depending on the composition of the feed material. And anaerobic digestion consists of a number of complex biochemical reactions carried out by several types of microorganisms. Okay, so when we were talking about composting or vermicomposting process, there were also presence of some microorganisms. In case of anaerobic digestion process, there will be also the presence of the different types of microorganisms. Okay, so the material left after anaerobic, so it during the this process, the biogas generation will takes place. Okay, and this biogas generally contains the amount of nitrogen, CH4, ammonia gases, ammonia gas, and H2S or H2 vapors. Okay, so this biogas can be used as a fuel source for because of the presence of the CH4 and H2 gas, which is having very high calorific value. So the material left after anaerobic digestion process is called digestate, which is rich in nutrients, and this digestate can be also used as a compost material. Okay, so in anaerobic digestion process, we are creating two different streams. Like one is biogas, and second valuable stream is the digestate. Okay, and that this digestate is defined as a wet mixture that can be separated into a liquid and a solid material. That solid material can be used as a compost material, or that liquid material can be used for some other purposes. Okay, so so for anaerobic digestion process, we are going to need a digester. Okay, we will put our organic matter into that digester. During that digestion process, that will create two different things. One is biogas, then second is digestate, and this biogas can be a source for heat or electricity generation, or it can be uh, converted into the gas grid or biofuels with the via biomethanation process. Okay, so when we talk about the generation of CO2 and methane relationship during the digestion process, okay, so if the amount of CO2 is on a higher level, okay, like we can see in the graph at 44% of CO2 content, there will be no burning. Okay, so CO2 content produced during that anaerobic digestion process has to be lower than the 44%. So, in case of anaerobic digestion, as we are not providing any external oxygen content, so the CO2 content will be the CO2 generation will be on the lower side as compared to the composting or vermicomposting process. So there are four stages of anaerobic digestion process. One is hydrolysis, then followed by acidogenesis, ectogenesis, and methanogenesis. So in the hydrolysis process, the hydrolytic bacteria using extracellular enzymes, and then acidogenesis process, fermentation will be there with the help of acidogenic bacteria. Then acidogenesis, there will be acting a acidogenic bacteria, and then methanogenesis process, the methanogenic bacteria will convert the uh, material into the CH4 gases. Okay, so in the first process of hydrolysis, the primary decomposition of the organic matter will takes place, and then in the following steps of acidogenesis and ectogenesis, the the decomposed organic compound will further decompose into the lower chain hydrocarbons, and at the end in the methanogenesis process, the higher chain hydrocarbon will get decomposed into the CH4 gases, which is useful for the biofuel generation. So there are some roles of microbe in anaerobic digestions, like acidogenic bacteria will convert that biomass into H2, CO2 and CH3COOH, and it will also convert the biomass into propionic acid, butyric acid, alcohols, etc., which will be in the liquid form. Then the acetogenic bacteria will convert that liquid content of propionic acid or butyric acid, whichever has been converted from the biomass, will convert that acidic content into further gaseous components like H2, CO2 or 3H3COOH. Then after that acetogenic bacteria, the methanogenic bacteria will convert these H2CO2 and CH3CO gases. Majorly, we can say CH3COOH gas will get converted into the CH4, which is uh, uh, which is going to be a part of the biogas containing H2CO2 and methane gas. Then the COD balance in anaerobic digestion, like that will be 10% will be the sludge percentage and 90% biogas will be produced. Then biochemical reactions involved with each stage of anaerobic digestion process. In the hydrolysis process, what will happen? The higher chain compounds are going to react with the water content, and that is going to be converted into the C's, we can say in this process, insoluble complex organic materials such as proteins, polysaccharides, and fats are converted to soluble monomers such as peptides, fatty acids, and saccharide. It is a very slow process, or we can say it is the rate limiting step in the anaerobic digestion process, because that will be the slowest one. Then this biochemical reaction involved like NC6H10 H10O5 plus NH2O will go into the hydrolysis process and convert into the glucose. Okay, and we already know that glucose is easily soluble in the water. Okay, then during the acidogenesis process, this converted glucose is going to get converted into simple molecules like acetic acid, or maybe we can say propionic acid, butyric acid, valeric, or isovaleric acids. Okay, so this glucose is going to get further decomposed into the acid formers. Okay, then in the active genosis process, this what will happen in this process, the products of acidogenic stage, okay, atoms, alcohol and fermentation product are converted to acetate, H2 and CO2 by acidoactogenous bacteria. Based on metabolism, there are two groups of acidogenic bacteria: proton reducing acidogenic bacteria or H2 forming bacteria generating acetate, CO2 and H2, or acetate oxidizing bacteria or acetogens catalyzes acetate conversion to CO2 and H2. Okay, then in the methanogenesis process, this the acid produced during the uh, first processing step is going to further converted into the CH4, CO2 or H2O. Okay, then there are some factors which affect this anaerobic digestion process, like temperatures. Okay, so temperature plays a major role during the physical and chemical properties of a substrate, which affect the thermodynamics and kinetic reactions inside an anaerobic reactor. Okay, so there are three different process during the anaerobic digestion process. One is psychrophilic, mesophilic, and thermophilic phase. So these phases are dependent on the temperature, and these phases represents the increase in CH4 generation during the methanogenesis process. Okay, so in psychophilus process, the temperature will be at around up to around 0 to 20 degrees Celsius, and the CH4 generation will be at around 20 to 30% only. While in the mesophilus phase, the temperature will get further increase up to 50 degrees Celsius, and the methane generation will be around at 40 to 50%. While in thermophilus phase, the temperature will become greater than 70 degrees Celsius, and the methane generation will be at around 90 to 100% at maximum. So rate of a reaction doubles for every 10 degrees Celsius rise in temperature up to an optimum, after which reaction rate declines rapidly. Okay, then thermophilic temperature range generally has several effects over the lower ranges. Some positive effects are increase in hydrolyzed soluble product, which make them more accessible to microorganisms. Okay, so during that thermophilic process, the peptide, the protein and other contents of the biomass is going to get converted into the peptides and glucose material. Okay, which are basically water soluble, and these glucose materials are more feasible for the microorganisms for the further decomposition process. Increase reaction kinetics in both chemical and biological process, shortening the reaction time and hence the hydraulic retention time of the reactor. It also increase the reaction kinetics in both biochemical and biological process. Then it improves the physiochemical properties of the soluble substrate, and there are some negative effect also for the temperature during that thermophilic temperature range. It increase the fraction of free ammonia, which is inhibitory to microorganisms, because uh, in the previous lectures we have already discussed about the effect of ammonia generation. So if the ammonia generation will be on the higher side, okay, so microorganisms will not be able to decompose the material because their life span will become lower. Due to that ammonia formation, the temperature will go on the higher side, and due to that high temperature, the microorganisms will not survive during the process. So ammonia invests the whole process dynamics and may hamper the quality of the gases. High accumulation of BFAs occurs which affect the growth rates of methanogens. Then for mesophilic temperature range, the advantages are greater process stability and better richness in anaerobic bacteria generation. Then some disadvantages are provide lesser biogas yield in comparison to thermophilic anaerobic digestion process. So optimum range for AD can be hydrolysis in thermophilic range and methanogenesis in mesophilic range. But various other factors also need to be ascertained before deciding the range of temperature for the anaerobic digestion process. Like pH has to be considered for the proper anaerobic digestion process. The methanogens are effective in a pH range of 6.5 to 7.5. So we have to maintain that pH range during the whole anaerobic digestion process. And this pH varies due to the temperature such as BFA, bicarbonate concentration and alkalinity of the system, and also by fraction of CO2 produced during the AD process. Because if CO2 generation will be on the higher side, that will convert the material into the carbonic acids, and that will lower the whole pH of the system. Okay. So one of the risk for digester failure may be related to the excessive accumulation of volatile fatty acids in the biogas digester. The acidogenic bacteria then flourishes, lowering the pH value up to 5.0 and inhibiting growth of methanogens. pH greater than 8 proved to be toxic to most anaerobics, which inhibits biological functions of the AD process. So we have to maintain that pH value in the range of around 6.5 to 7.5 for proper anaerobic digestion process. Then coming to buffering capacity, okay, that is known as alkalinity. An anaerobic digestion process has its own buffering capacity against pH drop due to the production of alkalinity during the AD process. For example, degradation of protein present in any substrate release ammonia content, which reacts with carbon dioxide producing ammonium carbonate, and this ammonium carbonate has a basic or alkaline nature, uh, which will result in the increase of the pH value of the AD process. Like it will with the help of this ammonium carbonate, the pH value of anaerobic digestion process can go up to 9 or 10 or 11 pH. Okay, so for while on the other hand, the degradation of salt of fatty acids may also produce some alkalinity, like shown in reaction CH3 COONA plus H2O is going to get converted into CH4 plus sodium bicarbonate content, and that is also uh, possess alkaline nature. Then there will be some sulfate and sulfide reduction, and it will also generate the alkaline nature, the reaction of which can be shown below. When pH in an anaerobic system drops due to BFA accumulation, the alkalinity present within the system neutralizes the acid and prevents further pH drop. So these reactions are going to provide the buffering action during the whole anaerobic digestion process due to the decrease in pH value due to the CO2 generation process. Okay. Then coming to carbon and nitrogen. Nitrogen is the major nutrient required for the growth of microbes and the synthesis of amino acids and proteins, which in turn converts into ammonia, a buffer compound for the neutralization of the acidification process. So nitrogen content is necessary in the feed material because that will provide the conversion of ammonia during the process. If the nitrogen content is low, microbial population remains less and it might take longer duration to digest the available carbon present in the substrate. While if the nitrogen content is high, then excess nitrogen leads to production of too much ammonia, and that will increase the pH value of the whole system into the basic range. Okay, and that will inhibit the anaerobic digestion process because microorganisms will not be able to survive in uh, very high acidic condition or very high basic conditions. So carbon serves to be source of energy and nitrogen controls the microbial population. So we have to maintain a proper ratio of carbon and nitrogen during the AD process. So that carbon and nitrogen ratio has to be between in the range of 20 to 35, and which is most suitable for various types of substrates. Then next factor is organic leading rate. So is defined as the amount of volatile material that is fed into an anaerobic reactor. So high OLR alters the digester environment, inhibiting the microbial activity during the initial stages of acid fermentation. Then increase OLR, increase acid formers. Okay, so we have to maintain the optimum value of these organic leading rates. So OLR therefore should be optimized based on the type of feed stocks and also the reactor temperature. Then HRT, hydraulic retention time. HRT is the average time that the organic substrate remains in the digester, and HRT also affects the biological and chemical properties of the organic substrates. It plays an important role in AD process, especially for methanogenic bacteria in mesophilic temperature, and it is desired to be long enough to provide sufficient methanogenic activities. Okay, then there is one more factor, volatile fatty acids. So fatty acids has to be maintained for the formation of the acetic acid because these fatty acids are only responsible for the acidogenic process producing the acetic acid, butyric acids, and these acids produced during this the acidogenic process is going to get converted into the methane gas during the methanogenesis process. Okay, so we need a optimum amount of acetic or butyric acid formation of acetic acid and butyric acid during the process for the proper formation of the methane gas. Otherwise, if there will be lower formation of acetic and butyric acid. So what will happen? There will be much lower formation of the methane gas, and that will result in the increased amount of the CO2 gases in the gas produced during the whole AD process. Okay, and we have already discussed that if the amount of CO2 gas increase more than 44% during the biogas formation, okay, that biogas will not be suitable for the burning process. Okay, so we need a optimum content of volatile fatty acids during the process. Then if we see the relationship of volatile fatty acids with alkalinity, so VFA will uh, control the alkalinity of the process with the time. Okay. Then okay. Then coming to the second lecture of the week. So after taking after maintaining the factors affecting the anaerobic digestion process, there are some pre-treatment and co-digest pre-treatment processes also, which needs to be performed on the feed. Okay, whatever feed we are providing for the anaerobic digestion process, there are some pre-treatment techniques which helps in increasing the biogas formation during the anaerobic digestion process, or we can say these pre-treatment techniques helps maintaining the proper anaerobic digestion process with the help of different factors. So pre-treatment process is defined as a process of initiating or improving the efficiency of microbial attack on a substrate, or we can say biomass. During the pre-treatment process, the compact structure of biomass is disrupted and exposed to microbial attack. Then there are three different types of pre-treatment process, which are physical, that can be done by the comminution or irradiation. Like in the comminution process, we are going to grind the material to lower size. Okay, that converting the material into lower size will result in the increased surface area for the microbial action. Then there is some irradiation process also, which will help uh, the generation of pores onto the surface of the biomass, which will help in the improve efficiency of microbial attack. Then there is some chemical process, like we can do some alkali acids or wet oxidation processes. Then biological processes are also there, with the help of which are performed with the help of fungi or enzymes for the improvement in microbial attack on the biomass substrate. The pre-treatment technology ensures biomass disintegration and improves solubilization in order to overcome the biological limitations of anaerobic digestion process. Through pre-treatment of any substrate, not only biogas yield can be increased, but also higher calorific value of the gas can be obtained, leading to less effort in purification for biomethane production. Then why there is a need for pre-treatment process? So pre-treatments are necessary when readily biodegradable and soluble organic matter, which will lead to the lower digestion rates. So rate of hydrolysis through conventional aerobic digestion is lower, resulting in higher HRT of digester, and larger digester capacity or volume is required for the proper decomposition process, and it will result in lower biogas yield. So effect of pre-treatment on different types of substrate. There can be various types of substrate from which biogas can be produced. Some of them are they can be lignocellulosic biomasses, which include some crop biomass or crop residue or energy crops or various types of weeds or organic waste. Then effect of pre-treatment of lignocellulosic substrate. So lignocellulosic biomass has a diverse composition, which includes more amount of the complex structure. It is having very complex structure which is resistant to disconstruction or microbial degradation. While if we compare these lignocellulosic biomasses with cellulose or hemicellulose or polysaccharides, that can be hydrolyzed much easier as compared to the lignocellulosic biomass. Okay, so the cellulose or hemicellulose can get converted into the sugar form much readily compared to the lignocellulosic biomasses. So lignin supports the cell structure, embedding cellulose and hemicellulose, hindering the susceptibility to microbial attack during hydrolysis process of anaerobic digestion. So pre-treatment breaks that lignin layer. Okay, that lignin layer has to be break so that microbial organisms can attack the cellulose or hemicellulose content inside that lignin layer to convert those cellulose and hemicellulose content into the glucose part. So that glucose part can go into the methanogenesis or acidogenic process for the further conversion of the biomass into the biogases. So pre-treatment also decreases the crystallinity of the cellulose and increases the porosity. So due to this increased porosity, the microbial action will become much higher due to the increased porosity. So food waste can be easily degraded but result in low biogas yield due to the presence of inhibitors or necessitating uh, which necessitate the pre-treatment processes. Then after lignocellulosic biomass, there is one more biomass content, that is sludge biomass. So the sludge biomass can be further divided into the industrial sludge or municipal waste treatment sludge or animal manure, including cattle dung or cow or some other dungs. Sludge from various types of processing industries such as food processing industry. So what is the requirement of pre-treatment on these sludge biomasses? The sludge biomass from wastewater treatment have high organic content. Okay, so secondary wastewater sludge consists of numerous microbial cells, and the walls of these cells act as a barriers against exoenzyme degradation. Okay, in activated sludge flock structure, exocellular polymeric substance which is known as EPS, comprise a major organic fraction, and binding mechanism of EPS to cations happens to be a significant factor determining the digestibility of activated sludge. So we need a therefore hydrolysis step becomes rate limiting step, and degree of degradation is limited around 30 to 35% COD reduction in conventional anaerobic sludge treatment. So with the help of the pre-treatment process, we can rupture this cell wall, and due to the rupture of cell wall, what will happen, the inside material will be will come into the picture for the further degradation during the anaerobic digestion process. So the pre-treatment of sludge ruptures the cell wall of sludge flock structure and facilitates release of intercellular matter into aqueous phase, which results in improving biodegradability with lower retention time and higher biogas yield. Then there are some non-conventional biomasses also, like algae content. So algae are capable of using sunlight and carbon dioxide and produce protein, carbohydrates and lipid through photosynthesis process. So microalgae biomass supports higher photosynthesis efficiency, higher biomass, which results in higher biomass yield and higher CO2 fixation than compared to plants. Biogas production has been considered the simplest bioconversion process to obtain energy from microalgae biomasses. So why we need the pre-treatment process on this microalgae biomass? The microalgae cell envelope is made of thick and hard layered composed of complex proteins and carbohydrates, and with more mechanical power and high chemical resistance, restricting the attack of biopolymers by methanogenic bacteria during the anaerobic digestion process, which inhibits the formation of the biogas during the anaerobic digestion process. Pre-treatment will improve the liquefaction process by biopolymer release enhancement and leads to stabilization, solubilization of the organic fraction. And after the solubilization of the organic fraction into the liquid, that will increase the efficiency of the hydrolysis process, so that this microalgae can be converted into different types of acids like acetic or butyric acid, and further will be vulnerable for the methanogenesis process for the formation of the biogas. Pre-treatment should be carried out at mild conditions to prevent excessive sugar degradation. Okay, we don't need excessive sugar degradation also, so that has to be carried out at some mild conditions. So there are some different types of pre-treatment processes, like mechanical pre-treatment. With the help of mechanical pre-treatment, we can decrease the size of the particle, resulting in the increased surface area for the microbial attack during the acid AD process. And then which we have already, so reduced particle size will increase in the specific surface area, resulting in increasing enhanced enzyme degradation. And so some mechanical pre-treatment processes are knife mills and shredders and or hammers mills, or we can go with the ultrasonic treatment. So during the ultrasonic treatment, the size will become lower with the help of the ultrasound treatment. Then coming to thermal treatment pre-treatment processes. So the substrate is preheated up to around 125 to 190 degrees Celsius and held at that temperature for a particular duration. In the laboratories, this can be carried out with the help of autoclaves, hot air ovens, or water baths, or microwave heaters. Dry substrate needs additional water before thermal treatment. So we have to add some water content in the dry substrate for the proper thermal treatment. In lignocellulosic substrate, the presence of heat and water disrupt the hydrogen bonds that hold together crystalline cellulose and the lignocellulosic complexes, causing the biomass to swell. And during this swelling process, what will happen? The pores will generate on the surface of that substrate, which will help the enzymes, which will help the microbes to attack on that biomass during the acid anaerobic digestion process. Then there are some chemical pre-treatment processes also. In chemical pre-treatment, uses a range of different chemicals like mainly acids or base of different strength under different conditions can be used for chemical treatment process. So chemical treatment processes can be categorized in three different categories. One is alkali pre-treatment. So that alkali pre-treatment is carried out with the help of different alkalis like lime water or sodium hydroxide or calcium hydroxide water. Alkali addition causes swelling of lignocellulose and disruptions of lignin with partial solubilization. So with the help of alkali treatment, what we are doing, we are trying to exaggerate the hydrolysis process of the lignocellulosic biomass. Okay, so it will take much lower time during the anaerobic digestion process for the hydrolysis step. And we know that hydrolysis step is the rate limiting step during the anaerobic digestion process. So that will, if we are going with the alkali pre-treatment process before anaerobic digestion process, so that will result in the lower time in the AD process for hydrolysis, and it will increase the efficiency of the anaerobic digestion process for biogas yield. In acid pre-treatment process, the lignocellulosic substrates will be subjected to the acid treatments with the help of some inorganic or organic acids. So acid pre-treatment does not disrupt lignin but breaks hemicellulose and disrupt other ether bonds between lignin and hemicellulose, which will result in the swelling of the uh, substrate, which in turn result into the proper hydrolysis process during the AD process. Then coming to oxidative pretreatment, it uses hydrogen peroxide or ozone for the oxidative treatment. So, but major disadvantage with this process is too much oxygen into the system increases the proportion of CO2 during the anaerobic digestion process, which will result in the uh, higher amount of CO2 gas component in the resulted biogas. And we know if the CO2 content is getting higher than 44% in the resulted biogas, okay, that biogas will not be suitable for the fuel purpose. Okay, then coming to the biological pretreatment processes, biological pretreatment process involves using microbial agents like bacteria, fungi, and enzymes for biogas enhancement from substrate. So complex biopolymers such as proteins and carbohydrates can be transformed into simpler end products due to the action of various enzymes produced by the bacteria during the biological pretreatment process, which in turn solubilize the organic compounds present in the biomass with minimum energy during the AD process. So hydrolysis process will become much easier after the biological pretreatment processes. So biological pretreatment with microbial agents lead to an increase of 29.54 percent in biogas yield as compared to non-biological processes. But these processes are much slower than non-biological processes. Biological pretreatment is applied by using direct microorganisms as well as enzymes extracted from microbes as catalysts to modify and to degrade the complex biomass polymers. So there are different types of biological pretreatment processes like anaerobic microbial pretreatment or aerobic microbial treatment. So it is clear with the name. In the case of anaerobic microbial treatment, we will not provide any air content during the biological pretreatment process, or in aerobic microbial treatment, we will provide some air, extra air content during the whole processing. Then there is fungal treatment, which is done with the help of the different types of fungi. Then there are some enzyme additions. Then there is co-digestion process. So in the anaerobic, we have learned about anaerobic digestion process. Then there is one anaerobic co-digestion process, which is known as NCOD. So NCOD is simultaneous anaerobic digestion of a homogeneous mixture of two or more substrates to overcome the disadvantage of monodigestion and improve the economic viability of the anaerobic digesters. So use of co-substrates improve biogas production and methane yield due to establishment of positive synergism in digestion medium. So what we are doing, we are going with two different types of substrate during the anaerobic digestion process. So if there is a deficiency in one substrate, okay, so that deficiency will be complemented by the another substrate. So we are going with the two different substrate having different properties which are useful for the whole anaerobic digestion process. Okay, so that process is known as the anaerobic co-digestion process. So in this process we can skip the requirement of the pre-treatment or the alkali treatment, like pre-treatment, different types of pre-treatment processes, and it will also improve the biogas production and methane yield. Then substrates having high CY/N ratio, monodigestion has poor process stability. Like we have discussed that CY/N ratio has to be in between 25 to 35. If we are having some substrate which is having a very high CN ratio like 45 or 50, okay, they these substrate cannot be digested properly during the anaerobic digestion process. So we can mix these high CY/N ratio substrate with some low CY/N ratio biomass, and we can enhance the whole biomass degradation process during the anaerobic digestion. So there are some factors which affect this NCOD process, like chemical composition of the substrates. So we have to we have to properly characterize the chemical composition of different substrates, which will will be mixed during the anaerobic NCOD process. Classifying the substrate according to their biochemical composition can be useful to evaluate bioaccessibility, biodegradability, and bioavailability of the substrate. There are different factors that affect the biodegradation of organic substrates, such as bioavailability, bioaccessibility, temperature, pH, moisture, nutrient concentration. So we have to mix the two different biomass substrate according to these different properties, and what is the requirement what is the optimum requirement for the anaerobic digestion process. So then coming to temperature, pH values, so temperature has to be in the optimum range, and we have to mix two different types of biomasses which can improve the temperature profile of the anaerobic digestion process. Then pH value has to be in the range of 6.8 to 7.2. Then coming to the CY/N ratio, that has to be maintained in between 20 to 30. So we can add higher CY/N ratio with some lower CY/N ratio biomasses, so we can get a optimum value of CY/N ratio in between 20 to 30. So now we will go with some question and answers. Okay. So first question is, why is pre-treatment done for a substrate in the anaerobic digestion process? So will it increase biomass integration? No, but it will definitely going to increase the biomass disintegration process. Okay, so pre-treatment is generally done for the biomass disintegration process. Like we can convert the uh, we can decrease the size of the biomass, or uh, we can we can say we can destroy the surface layer of the biomass, so that it can be easily decomposed during the anaerobic digestion process. Then it will also improve the solubilization during the anaerobic digestion process, because uh, if we are going with the lignocellulosic biomasses, okay, so without the pre-treatment process, the during the anaerobic digestion, it will take a very high time for the hydrolysis process. And if we are providing some pre-treatment processes on that lignocellulosic biomass, so what will happen, that pre-treatment process will destroy the lignocellulosic layer, that will so that inside hemicellulose or cellulose layer will become vulnerable for the microorganisms during the anaerobic digestion process, and that will improve the solubilization of the cellulose and hemicellulose content during the hydrolysis process of anaerobic digestion. So answer is B and C. Then what is the percentage composition of hydrogen in biogas from the anaerobic digestion process? So that has to be in the range of around 0 to 1 volume percent. Generally, the composition of biogas contains a major amount of CH4, around 70 to 80%, and 60 to 70%, and CO2 gas around 20 to 30%, and there will be some other hydrocarbon gases also will be there in the biogas composition. Then third one, pre-treatment of sludge during the anaerobic digestion process is done to for increasing the retention time, lower biogas yield, or improved biodegradability, or increased biogas yield. So pre-treatment of sludge, it will not increase the retention time. Uh, Contradictory, it will decrease the retention time of the sludge during the anaerobic digestion process after the pre-treatment. Then lower biogas yield, no, that will be the vice versa. It will increase the biogas yield after the pre-treatment process. Improve biodegradability, yes. The pre-treatment process will increase the biodegradability of the sludge during the anaerobic digestion process, and it will also increase the biogas yield during the AD process. So these are the answers C and D. So what is the sequence of anaerobic digestion process? So the first one, there were four different steps, four major process during the anaerobic digestion process. First one was hydrolysis, then followed by the acidogenesis process, followed by acetogenesis process, and then methanogenesis process. So answer is C. The optimum range of pH during methanogenesis, that has to be in the range of 6.5 to 7.5, because more acidic or more basic pH during the methanogenesis process will decrease the life of the methanogenic bacteria, and it will result in the lower formation of the CH4 gases during the methanogenesis. What is converted to peptides in the hydrolysis process of anaerobic digestion? polysaccharides, proteins, fats or fatty acids. So during the hydrolysis process, generally the protein is responsible for the conversion of the peptides. The polysaccharides will directly go into the form of cellulose and hemicellulose, then again into the glucose part, then fatty acids, fats or fatty acids will result in the formation of more ammonia due to the higher nitrogen content. So these during the hydrolysis process, the protein is going to convert it into the peptides, and this peptides is going to convert into the uh, butyric or acetic or propionic acid during the acidogenesis process. Then high levels of simple sugars result in VFA accumulation, increased pH, increase in methanogenesis, or none of these. So high levels of simple sugar will result in the VFA accumulation during the anaerobic digestion process. It will not increase the pH value because simple sugar is not going to convert it in it's simple sugar it is generally C6H12O6. Okay, so that is not going to create any ammonia during the acidogenesis or we can say hydrolysis process, so it will not increase the pH value, or it will also not increase the methanogenesis process, so it will result in the VFA accumulation. And what are the disadvantages of the Deen Bandhu biogas digester? More leakage, no it the this is the advantages of Deen Bandhu biogas digester, that there is very less leakage and it has very high stability and very low recurring cost. So these all are any of these are not the disadvantages of the Deen Bandhu biogas digester. So answer is none of these. Floating drum plants consist of moving gas holder, static gas holder, guiding frame, or none of these. So floating drum plant basically consists of moving gas holder, and for uh, this moving gas holder is consisted with a guiding frame. So that has for we can say for holding the moving gas holder from tilting. Okay, so with the help of guiding frame, that will prevent the tilting of the moving gas holder into that in the floating drum plant's biogas digester. What percent of methane formation is from acetic acid? So acetic acid can form around 70% of methane gas during the anaerobic digestion process with the help of acetic acid. Okay, so that is for today. So now we will end this meeting.